Hello, my name is Guilherme, and I'm an engineer at PSR, and today I'm going to talk about some recent developments in ParametricOptInterface. This is a package for dealing with parameters in the JUMP ecosystem. So this project was a joint work with Invenia Technical Computing, and I would like to thank the team at PSR and at Invenia. In particular, I would like to thank my project colleagues, Joaquim Garcia and Rafael Benchmal, that also put a lot of time and effort in this project, in the development and coding of these improvements. So the first thing is to talk about what are optimization problems with parameters. So oftentimes practitioners in mathematical programming, they must build some optimization problems, solve them, query some of the results, make some small changes to the same problem, and solve them again. Well, this process of modifying and solving the problem can be repeated many times. And there are some applications where this appears quite often. So some examples are Bender's decomposition, progressive hedging, stochastic dual dynamic programming approaches to solving problems, and differentiation of complex optimization problems where you have to try to understand the sensitivity of some parameters. Well, to illustrate the presentation without explaining the cumbersome applications, which can be quite difficult, let's just consider a small example of economic dispatch, where you have some costs of generation and some generation capacities. And we have some stochastic demands. So for example, 1,000 scenarios of demand, and this is a quite common power system example, where we have to deliver all the energy at the minimum cost. We have an objective that is the total cost of generation plus a deficit cost. We have some capacity constraints, and we have a load balance constraint where we have to attain this demand that varies in 1,000 scenarios. You can see that to solve the 1,000 different problems, well, the problem itself, the structure of it changes very little. It only changes the right-hand side of a certain constraint. So we could exploit like some possible implementation approaches to solve this in real life. The first one I'm going to talk about is the most naive one, which is simply to declare the problem entirely and solve it 1,000 times. While this is very clear and avoids bugs and mistakes, it is not quite performant because you have to re-instantiate the solver, you have to redeclare all the variables, and so on. So another possible way is to modify just the right-hand side of the constraints directly. And this way, it is quite performant, it is quite good, but it's not very robust, and it is very easy to input some new bugs because it only changes the right-hand side. So if your right-hand side is an expression of different parameters, or if a certain parameter appears in a lot of constraints or in a lot of places in your model, you have to keep caches about where the parameter appears, and you will have to make a lot of glue code just to make this performant and robust. So this is a different approach that you could take. A third one, it is to add some equality variables that allow you to keep a reference for a parameter in your model. And then when you have to update the values of your parameters, you simply just update them using the JUMP interface. And this is quite okay, it's very robust, but it adds new constraints and variables to your model. So it can lead your model to being bigger and slower to solve. And the ParametricOptInterface approach to declare through the JUMP interface that, well, you have a reference that acts exactly like a variable, but you inform that it is actually a parameter. So it won't be lowered as a variable. It won't add a new variable and a new constraint to the solver underneath, but it will keep the reference. And so with this, when we later try to update the parameters, we can query exactly where the parameters appear and apply the correct functions, such as some coefficient modification or some updating of the right-hand side where we already calculate all the parametric expressions that might appear. And well, the advantages of using the ParametricOptInterface approach is that allows users to have a robust implementation of the good practice such as performance-wise, and avoid bugs regarding caches and the process of updating the values of parameters. Another advantage is that it works interacting directly with MathOptInterface, so it should work with every source with compliant to the MathOptInterface that has a MathOptInterface. And it also requires a very minimal new syntax to work on, to learn if you are already used to the jump way of declaring your problem and so on. So some features of the package. Well, the package is very flexible, so it lets users add parameters in many places of the model. So here we have an example. We have a mathematical problem, and every place where we have a parameter data is where you can add parameters using this package. So it is quite flexible. Another feature is that users can query duals of the parameters, which is oftentimes useful in algorithms such as Benders decomposition and stochastic dual dynamic programming. And a new feature that we like to highlight is that it has a brand new documentation. So this documentation has a lot of step-by-step and how-to guides, and it is quite useful when dealing with parameters. So in our small experience so far, it has helped a lot some users to identify what they need to do. And well, the parametric interface is quite customizable, so it allows users to make a lot of choices and turn off some features that can speed up your process of resolving the problem and allocate less memory. So some small examples on one side is that you can skip the part of population, the parameters, the dual of parameters. You could also not save the original expressions and objective constraint of objectives and constraints. So only storing the versions of the model where the parametric expressions are evaluated and turned out as a real number, not as a reference to some variable. And some others that, well, you can see in the documentation. So just to clear up some performance benchmarks, here, since the start of the project, we were in version 0.3, and we declared some set of benchmarks that are available on the GitHub repository. And right now, we have 3 months of development, and we have managed to greatly increase the execution time of the benchmarks and decrease the allocated memory of our benchmarks. So we have been able to shave off a lot of the performance bottlenecks that existed. And just to say some final remarks, well, this is a jump extension that helps you implement this parametric interface applications. And the idea is that it allows you to use the best practices, avoiding bugs manipulating the parameter. So this is one of the main messages. And well, although POI can help you increase the performance of your parametric applications, it's not a silver bullet that will always work, but you can read the documentations for some caveats and tips on some other tools and other jump options that you could use to help you increase performance. And since it's a MOA extension, well, parametric interface can be integrated with other packages in the jump ecosystem, such as dualization and diffop. So final summary, the main idea is that, well, it's friendly. You don't have to learn a lot of new syntax. It is quite robust, and it is very low cost. It doesn't add a lot of burden, and it's not very different from making a good implementation of caches and modifying right-hand sides and modifying matrix coefficients inside your optimization problem. So the idea is that it's friendly, robust, and it is a low-cost dependency and a low-cost way of doing things without adding bugs. Okay. So thank you very much.